Apologies, PowerPoint changed how they record slides on me. So this is work done with Prasoon Dewan at University of North Carolina at Chapel Hill. And in particular, it's focused on a step towards intelligent CSCW, where users interact with an intelligent collaborative system, which predicts the actions of those users and others. And in the context of this session, we're focused on the recommendation piece. In particular, we're making recommendations for the specific problem of user selection. Where in this problem, users must decide with whom to share information. So for example, you may have to select recipients for an email, choose who has access to distributed files, folders or files, distributed file systems. In social networks, choose who has access to posts, or in instant messaging, choose who has access to or who you're chatting with. And this is a problem because, as past work has observed, there's instances of under and oversharing. For example, in the case of undersharing, past work has observed users chose not to share possibly helpful health information on Facebook, and a large portion of emails in a study did not correctly contain a desired recipient. For example, some emails only contain professor when they should contain a TA. There are also examples of oversharing, such as 91% of the top 150 Facebook apps were unnecessarily given access to private data. And Michelle Bachmann, a US politician's staffer, accidentally was addressed in an email critical of her. And this is actually part of a more general problem of selecting items from a list of options, where the main issue in this general problem is human memory, and that users must recall all possible options, such as numbers, letters, or things like email addresses, and they must recall whether to select each option. And past work has identified specific issues in this general problem, namely that users can only correctly remember a limited number of digits, letters, or words, and users only specified a portion of binary or ternary features of phonemes correctly. If we treat whether to include an item or not as a binary feature, we can assume that users will specify a portion of those incorrectly as well. So how can we reduce these issues? Well, one obvious approach is to offload to computer memory, where you have a list of options and you read through them and select them as you go. And this is used in many email clients like Gmail and Mozilla Thunderbird, so it applies to this problem, but it's infeasible for large lists of recipients. A more subtle approach found by past work is grouping, which reduces human effort. So users were found to more easily remember grouped rather than ungrouped items. So for example, it may be difficult to remember all these characters, but if you sort them into words, it becomes much easier to remember them. And users can make decisions at the group level, therefore making fewer binary decisions. So for example, choosing all the characters in one word and none of those in another. And this actually maps to a classic user selection problem solution of name groups, where name groups are semantically labeled groups of users. And these can be centered around various traits, context, topic, trustworthiness, and so forth. And for example, you can have a faculty search committee made of various members, and this can be used in various contexts, such as sending out a survey to that committee, or scheduling meetings via email, where the recipients of that email are replaced with are the members of that group. However, this grouping still requires effort, in that users must create, populate, and maintain these groups. And the larger the number of potential recipients, the more effort it is to do these tasks. So we see that effort increases as scale increases, and there are some systems that have high scales that lead to significantly high effort. This is even more exacerbated by the finding of past work that users tend not to fully solve an information security problem, like the user selection problem. If by doing so, they're better able to complete tasks. And these trade-offs may explain some observations we've seen in some other work too. Users didn't spend time learning to use friend lists or groups on Facebook, and most mobile users don't use existing functionality to group their contacts. And some other examples you've already pointed to of emails not containing desired recipients and emails containing undesired recipients. So how can we reduce this effort? Well, one approach is full automation, in which the system automatically performs the user selection problem without input from the users. And this is helpful in that it removes all effort from the user. But because users have no input, they can't correct the system as it is wrong. So an alternative approach is a mixed initiative approach, where both the system and the user take initiative in exerting effort. The system identifies tasks. The user then accepts, edits, or rejects those tasks. And the system only performs accepted or edited tasks. In other words, generating recommendations. And this is the focus of our approach. So the next question is, when should these recommendations occur? Well, if you're going to use name groups in some instance, such as addressing an email message, you'll somewhat obviously want to recommend group creation prior to when the name group would be used. And this is the focus of much of past work, and we refer to this as foundational name group recommendations. But name group usage can be more complicated than this. For example, after this email is sent, Another user, Alice, may join the department and the faculty search committee, and then a survey is sent out to that committee about candidates. As this implies, Alice should be added to the name group, or it should be evolved to include her. And this is the focus of our work, evolutionary name group recommendations. And as a basis for these name group recommendations, we'll use social graphs. In particular, we'll look at explicit and implicit graphs. Explicit are where a user explicitly adds or removes nodes to that graph by adding or removing users, such as on social networks. Implicit are inferred by shared communications. For example, the senders and recipients of a single email message would imply that those users are nodes in the graph with edges between them. And because we're using social graphs as a basis, we want to first look at how social graphs will evolve to inform how we'll evolve groups. Graphs can evolve by adding members, by adding nodes to the graph, removing members by removing nodes from the graph, or changing connections by keeping nodes the same but adding or removing edges. And because this is the first approach at evolutionary recommendations, we'll focus on the growth of social graphs and how their associated groups grow. And there are many methods we could do this type of evolution. We looked at manual approach, which involves no automation, but the user takes into account the current social graph, the old social graph, and old named groups to specify how groups should evolve. There's also a full recommendation approach we considered, which that doesn't take into account the old social graph or the old groups the user had created, but instead feeds the current social graph into a previously successful foundational name group approach, recommends a whole new set of groups the user can edit to generate a whole new set of groups that supersedes the old one. And finally, we considered a change recommendation approach, which takes into account all of the old social graph, the new social graph, and the old groups the user created to generate a set of recommended evolutions the user then can edit to generate the evolved groups. And our focus is developing this change recommendation approach. And within this change recommendation approach, we have identified two different types. A composed approach, in which the current social graph is fed into a foundational name group approach. This generates recommended groups, which are matched and merged with old groups based on the old social graph to generate recommended evolutions. This is good in that it leverages previously successful approaches, but because these previous approaches were tuned towards creation of groups rather than evolution of them, it may be less precise. In comparison, we looked at an integrated approach, which integrates all these into a single new approach, which may generate more precise evolutionary recommendations because it is tuned towards evolution rather than creation of groups. But it's likely to be more expensive because it doesn't reuse past work. We will focus on a composed approach, but because we are doing so, we need to define a match and merge approach and build our own algorithms. In particular, a match algorithm requires a similarity measure, which takes into account a similarity vector of additions, deletions, and expected new members, and a growth rate, which is essentially the number of new nodes in the graph divided by the total number of nodes in the old graph. And each potential pairing of an old group and a new group has two similarity vectors, an expected one, where we expect the user to have 0 adds and 0 deletes, but the growth rate to match the growth rate of the graph as a whole, and an actual similarity vector, which includes the existing members of the graph that are added, the existing members of the graph that are deleted, and the new members of the graph that are added. And then similarity is defined as the distance between these two similarity vectors. So given we have a similarity measure, what threshold should we use to determine matching? Well, we looked at low thresholds and found few but precise matches, and high thresholds too, but we found many matches, but many were incorrect and with low one-to-one matching rate. So to rectify these two problems, we've developed a multi-round matching approach, which initially has a similarity threshold of 0, matches groups that are similarities less than or equal to that threshold, then checks whether all old groups or new groups have been matched. If yes, we can stop. If no, we'll increase the threshold by 1, and we'll continue the cycle from there. To illustrate, consider an old graph consisting of 6 members and a new graph consisting of 8 members, which means the growth rate is 1/3. And a threshold is 0, and 2 old groups, research group and social group, which consist of 3 members each, and a recommended set of groups, A, B, and C, which are varying size. We first match any groups that have similarities less than or equal to our threshold of 0. We see research group has one such recommended A that it can map to, and social group has no such group, so it maps to nothing in this round. We map those two together, research group and A, and remove them from the pool of possible matches. Then check whether all old groups or new groups have been matched. The answer is no. So we increase the threshold to 1. Again, check for thresholds, and see in this case, social group cannot match. So we again repeat the process. And again, increase the threshold to 2. because all groups have matched. And now at this point, we see that social group matches to B because it has a similarity threshold less or similar than our threshold. This matches and is removed. Now all old groups have been matched, so at this point we'll stop. So since we've developed a matching algorithm, we again need to merge them. And recall our goal was to recommend group growth based on graph growth. So we analyzed our old groups and new groups in terms of this goal, where old groups consist of the previous user effort to create groups, and the new recommended groups can be broken into 3 pieces. The existing group members that match the old groups, additions and deletions of existing graph members, which we assume the user has already performed in previous creation and evolution of groups, and new graph members which we are explicitly trying to add to the old groups. So in this case, our merging is the old groups plus the new graph members. And now that we have defined an approach, we wanted to evaluate in terms of explicit graphs. So we have from this 2 data sets of social graphs at time tk from various accounts and new groups at that same time tk. What we need to do this evaluation is also a social graph at time tk-1 or past time and old groups at that same time. To do this generation of the old groups and old graph, we randomly selected nodes to remove from the graphing groups. And the number of nodes was chosen to match our goal vertex growth rate I mentioned earlier. And any groups with less than or equal to 1 member are treated as non-existent at time tk-1 because we assume that all groups are 2 or more members. We also wanted to evaluate in terms of metrics to measure the effectiveness of our approach. And we wanted to compare against manual evolution with full recommendation and composed. And there are 2 types of effort we analyzed: additions of members to groups and deletions of members from groups. In the case of manual, we expect the user has to manually add each new member. So we can do additions in terms of relative additions, or the additions to recommendations divided by the total number of manual additions expected. And in this case, less than 1 relative addition is better than manual, greater than 1 is worse. In deletions, in the manual case, the user expected to only grow groups, so no deletions are expected. So the total deletions is what we can count, and where 0 is the same cost as manual. And furthermore, we assume additions to be higher cost, because users are required to recall options, identify them, and input them, and deletions are lower because they must only identify and select items. We judge that composed perform better than full recommendation and manual approach based on these requirements when growth rate is between 0.2 and 0.5. We also wanted to consider implicit graphs, recall. So to do this, we developed our own evaluation and sampling process, where the first 80% of messages were broken up into old messages and new training messages, where the old messages were used to generate a graph at time tk-1, or the old time, and new messages were used to generate the graph at time tk. Then the last 20% of messages were reserved for test messages. And because we had test messages, we developed new metrics about uses in those messages, where we modeled recommendation acceptance rate, or percentage of evolved groups that would be cheaper to address in a message than using in any group from time tk-1, a perfect match rate in which a recommended group exactly matches the recipients of that message, and relative additions required to address a message with that group divided by recipients in that message, and relative deletions, which is same as relative additions but with deletions instead of additions. And we evaluated this in 3 different types of groups and 3 different data sets. Groups of email recipients in a previous study of 28 accounts on response times in email, groups of Usenet groups from the messages in 20 news groups, and groups of Stack Overflow tags or meta tags in the Creative Commons release Stack Overflow questions. And in these results, we found high acceptance rates, low relative additions and deletions, which are both good, however, low perfect match rates. And we found that composed never performs better than full recommendations, indicating it's about equal to creating new sets of groups. Throughout this talk, I have detailed various contributions. Namely, we've identified various types of social graph evolution, identified and qualitatively compared types of evolutionary recommendations, motivated, designed, and implemented a composed approach for recommending the growth of named groups. We've showed our approach to be applicable to explicit social graphs with growth rates between 0.2 and 0.5, cross-applied successful approaches in explicit social graphs to implicit ones, and we have also identified several remaining questions as a part of our work. Namely, do evolutionary predictions apply to other types of uses or of groups? Are there better ways to model the growth of explicit graphs? Are there better comparisons for evolutionary effort? And what is the perceived usefulness of evolutionary recommendations? And finally, are there types of evolutions that are more or less effective in specific contexts? For example, certain topics, contacting trusted individuals, or hierarchical relationships. because we treat evolution as a first-class issue, this provides a better basis for investigating these questions further. Thank you.
All right. So questions from the audience? So I did have one question. The approach relies on the social graph. So for example, with the email that you mentioned with the new faculty member added to the department, what would the social graph, how would that social graph have been derived in that case?
So in that case, you would assume that that new member would have communications with all of those existing members in one way or another. So they would kind of be, so you would see emails within the department of welcoming that member, seeing them as like communication of I want to join the faculty search committee with specific members of that committee, or communications of how do I find out about things. So you would see communications that are not official with it, but communication with existing members.
So it might not cover the case where the dean says, oh, we forgot, we should have someone from this department, let's add this person.
Yes, so that would actually require some manual addition of there, and so that's where this would fall short.
Okay. I'm thinking about it with my research group, where master students come and go, whether we'd be able to capture that. Because it seems like I communicate a lot more with people who are probably not going to join my group than with a brand new student who might join the group.
And I think it would be better in that case of, instead of, it might be better of subgroups within there, of you have certain master students centered around certain topics, and they would be communicating more about those topics, and you could better organize them around that.
Other questions or comments?
I have a rather simple question to your starting point of mixed initiative. So, and if you would, thank you. So if you would basically, how does your model change if basically the user starts the process and then you have a kind of turn taking over the, or if really the system basically finds changes and proactively starts a process? So taking this mixed initiative really literally and saying the impulse could come from a system or the impulse could come from the user.
Yeah, so I didn't address actually triggering of the recommendations, and that's a really good question. Of we could at one point detect that this is a period of social graph growth that is particularly good for a particular type of recommendation that is effective. So we could trigger for the user, you should run this algorithm and try and detect how your group should grow at that point. Or the user could identify themselves, I haven't looked in a while, I should see if my group should evolve. I think both of those cases are applicable.
While we're taking one last question, does the next speaker want to come?
I'm happy to.
You're going to come? And we can disconnect you?
Yes.
But while he's getting set up, if there's another question or comment.